Hello everyone. Today I'm going to be exploring classical versus quantum error correction using the Qubit Factory. Okay, so to begin with, we're going to look at classical error correction. Okay, so here we have a level in the Qubit Factory. Our goal is to simply send the inputs from A to the outputs at C. Okay, so let's try and do this and see what happens. Okay, so we have this row of question mark gates. And what these represent is some noisy channel. Okay, so most of our bits go through fine. Occasionally, at random, one will be flipped to the opposite state. Okay, so let's speed this up. Okay, and we see we do not pass the level. Okay, so we got 400 out of 500 correct. But in order to pass the level, we need to meet a much higher threshold. We need to get 440 out of 500. Okay, so how do we correct for these random errors that are occurring? Okay, so probably even if you've never thought about this problem before, there is a really obvious thing to do, which is why don't I just send more than one copy of my data? Okay, so that way if something happens to one of the copies, I could still use the other copy. Um, so let's do this and see what it looks like. So I'm just splitting my data into two at the moment. Okay, so each bit comes in, it gets split, and then they go through the noisy channel. Okay, and we see, so we have two ones. Okay, so we have a 1 and a 0. So what we know is that one of these bits must have been flipped. Okay, and we have a 0 and a 1, so again, one of these bits must have been flipped. But just having two copies doesn't actually help us in terms of correcting errors because we don't know, we have no information about what is the correct result. So what we actually need is at least 3 copies of our data. Okay, so I split so each bit gets duplicated 3 times. And now when I run this, okay, I should look at each column of 3 bits, and I have a 1 and a 1 and a 0. Okay, so this bit is most likely a 1 bit. Okay, so having two bit errors occur is much less likely than having 1 bit error occur. Okay, so for each column of 3, I should look at whatever the majority of the bits are, and that is the most likely case for what the original bit was. Okay, so what we have to do now is for each triplet of bits, we have to output whatever the majority of these bits are. And a simple way to do this is first I'm going to compare the bottom 2 bits together. So if these bottom 2 bits are the same, then this tells me that they represent the majority. If these bottom 2 bits are different, then whatever the third bit is represents the majority. Okay, so if the bottom 2 bits are the same, what I'm going to do is output the result to the exit. So if they are the same, which is represented by a 0, then they go to the exit. However, if the 2 bits are different, then they go to the incinerator. Okay, and now we want to do the opposite thing for the top. If the 2 bottom bits are different, then the top bit goes to the exit. If the 2 bottom bits are the same, then the top rail goes to the incinerator. Okay, so let's see if this works. Bits come in, we compare the bottom 2 bits. Okay, they were different, so the top rail gets output, and we see that we have the correct value and the correct value. So let's speed this up to see if this works in aggregate. And there we go. So 450 out of 500 correct, so we passed the level. You will notice, however, although we passed the level, we did not reach the bonus criteria, which required 480 correct. Okay, so how would we go about solving the bonus level? Well, this of course So it's relatively straightforward to generalize our strategy to include more duplicates of the data. However, it becomes a little bit of a challenge trying to fit everything we need in the space of one factory. But certain people like myself sort of enjoy this type of challenge of optimizing a process as much as possible. So for those of you who are interested, here is an example solution of a more advanced error correction strategy that will satisfy this extra threshold. And we can speed this up and hopefully it works. And there we go, 492 out of 500. So please try to beat me. I would like to see what designs other people come up with. Okay, so let's move on to quantum error correction. Okay, so we see we have a very similar level to what we had before, except rather than bits we have to transmit, now we have qubits. Okay, so let's just send them through our noisy channel and see what happens. Okay, so most of them are going to go through unscathed, but occasionally at random, one of them is going to be rotated. There we go, rotation. Okay, so speeding this up, we see that we get 73 out of 100 correct, which falls well short of the 85 out of 100 we need to pass this level. Okay, so how do we correct for these errors occurring? So the most obvious answer would be just to try to copy the classical error correction strategy. Okay, so why don't we just duplicate our qubits in the same way we duplicated our bits? And unfortunately, we just can't do this. Okay, so there's no equivalent of the splitter gate for quantum bits. Okay, and this is actually a theorem in quantum computing called the no cloning theorem, which tells us that we can't duplicate an unknown set of qubits. Again, and this is really weird when we think about it, because duplicating data, like copying a file, is something we do on regular computers all the time. We don't even think about it. So it's somehow strange that this is not something we can do with quantum data. Fortunately, there is an elegant solution to this. Okay, so rather than duplicating my qubits, what I'm going to do instead is entangle them with some ancillas. Okay, so what this means is I'm just going to generate some qubits in some known state, and I'm going to entangle these together with my data qubit. And so my data qubit comes in, and it gets entangled with my 2 qubits I generated. So now I have a 3 qubit entangled state. And so what I've done with this is I've distributed the information from 1 qubit amongst this group of 3 qubits. Okay, so if anything happens to one of these qubits in this group, then I can still potentially recover this data precisely because I've distributed it amongst multiple qubits. Okay, so what I'm going to do is on the other side of the channel, I'm going to undo this entangling procedure. So if no errors occur, this should bring me back to my original state. Okay, and what I'm going to do is measure the ancillas. Again, if no errors occurred, then I know these ancillas should be in the up state, so I know I should be getting a 0 coming back from the measurement. Okay, so let's play this out. Okay, and now I have a very similar scenario to what we had with classical error correction, where if I have a 0, if I have zeros, then I know that, I'm fairly confident that my bit is in the correct state. If I have a 1 on either or both of these ancilla measurements, then I know that some error has occurred that I need to fix. Okay, and before we go any further, what I'm actually going to do is use some dummy data rather than our actual data, just to make the correction a bit easier to understand. I'll put in a delay there just to spread things out a little. Okay, so now all of my data is going to be just qubits in a particular rotational direction. And we run this through, and we see that indeed if we get 2 zeros, then the qubits are in their original state. If we get 2 ones, then in order to get back to the known state, we have to flip on the x and the z axis. If only one of the ancillas is in the one state, then we know that we just have to flip along the x-axis in this case. Okay, so whether we have 2 ones or just a single one corresponds to different error types, and we can just see how to correct each type of error. So let's go ahead and do that. Okay, so I'm going to compare my 2 measurement results. Okay, so if either of these measurements is a 1, then I need to flip along the x-axis, which I will do there. And if both of them were a 1, which I am going to do with an AND gate, like this, then I need to flip along both axes, the x and the z. Okay, so let's just see if this works. So if this is working correctly, all of my qubits, or most of them at least, should return to this initial rotational state. Okay, so qubits come in, and indeed some of them are still wrong, but most of them look like they're working out correctly. Okay, so let's hook up our actual data, and we'll actually send things to the output, and again we'll include a delay just to avoid things bunching up too much. Okay, so qubit comes in, it gets entangled, it gets disentangled. We evaluate the ancilla measurements, and we see in this case we don't need to do any error correction. Both of the ancillas were 0, so the qubit just goes out, and indeed it matches the value it should match. Okay, so let's speed this up, and we pass the level, so 89 out of 100. However, we still fall short of the bonus criteria, which requires a much more sophisticated error correction strategy. So I can give you a preview of what this looks like. Okay, so here is one I prepared earlier, which basically follows the same strategy, except it uses more ancillas in this encoding and decoding procedure. So again, the strategy was not too different, but fitting this all in a compact design was a relatively difficult challenge. So I'll be interested to see what other people come up with in terms of error correction strategies. And let's just speed this up, and there we go, 97 out of 100 correct. All right, thank you very much. I hope you've learned something about classical error correction, how it differs from quantum error correction.